Another example is a combined Couette, Poiseuille flow. In this case, we're going to take the same two plates, and we're going to impose a pressure gradient, P1, P2. We're going to impose a dP by dx. It could be negative, could be positive, could be zero. And we're going to move this plate at the speed u wall. So the same conditions apply. We're going to assume steady state, Newtonian, constant properties, rho mu, and we're going to assume that there are no effects in the y and z direction, v equal w equals 0, and du by dx will be equal to 0. So so the only non-zero, so u is only a function of y, is u of y. Okay, so the same equations apply as we did before. We simplify the x momentum equation, and that gives us, so you see the previous example on the Poiseuille flow, but what essentially this does, it gives us the following equation: mu d2u by dy squared equals to dp by dx. So what do we expect here when we kind of want to sketch the flow? Well, if we didn't have any pressure gradient, the flow is gonna look like this, just a linear profile. And if we didn't have the plate moving, we're gonna have a Couette, a Poiseuille type problem, where the velocity profile is gonna look like this. Now, when you combine the two, you just simply not adding the two profiles, but you're actually kind of just dragging these fluid parcels over here with the plane, and then you're going to have something like this, possibly. Okay. Now, if the pressure gradient is switched, so in this is the case when dP by dx is negative, but what if dP by dx is positive? So flow is coming, there's backflow. Well, what's going to happen? You're going to have something like, if this is the zero line, you're going to have something that looks like this. Okay, and that is going to be dependent on dP by dx and on the velocity at the boundary. So very simply, we can integrate this. Remember, this u of y was 1 over 2 mu dP by dx y squared plus c1y plus c2. Boundary conditions. In this case, we're going to put the coordinates at the bottom over here, just because we can. And really, this flow is expected to be asymmetric, so there's no preference for where we're going to place y. So the origin, so we're just going to place it at the bottom of the channel. So over here, u at y equals 0 is 0 because the bottom plate is fixed, and u at the upper plate, u at h, is equal to u wall. Assume that the height over here in this case is h. So the first one implies that C2 is equal to 0. Great. The second one implies that 1 over 2 mu dP by dx h squared plus C1 h equals to u wall. We divide by h, so we get C1 is equal to u wall over h minus 1 over 2 mu dP by dx h. That is C1. From C1, we conclude that uy is equal to 1 over 2 mu dP by dx. We're going to factor things out. We will have y squared minus hy, because C1 is multiplied by y, so we have an hy over here, and plus u wall over h. This is an interesting form, but to get it into something that is a little bit more manageable, because we have so many variables here. We have h, we have so many parameters. We have h, dP, dx, mu, and u wall. I want to get this into a dimensionless form that we can plot regardless of what the channel height is, just into a dimensionless form. So what we do, we're going to divide by u wall. So we are plotting u star equal uy over u wall. and that will be equal to, and there's a y over here because we're multiplying C1 by y. So divide by u wall, you get y over h plus 1 over 2 mu dp by dx into, and there's a u wall over here, times 1 over u wall into y squared minus h squared. This is still not in a form that I like, although this whole thing is dimensionless. This whole thing is dimensionless. But what I want the coefficient to actually be dimensionless and turn this into also a dimensionless form. Because y over h now, that becomes a new coordinate, right? So what if we do the following? So this, you can verify that this has units of 1 over meter squared. Because this is meter squared, 1 over meter squared will become dimensionless as we expect here. So what I'm going to do next, I'm going to multiply and divide by h squared over here. Multiply and divide by h squared. What you get is y over h plus 1 over 2 mu u wall times dp by dx. And we're going to do an h squared over here. And we get y over h, y squared over h squared minus 1. Okay? And now, so yeah, we took h squared, so we multiplied and divided by h squared. We took h squared inside. So you can verify that this is a dimensionless quantity, and I'm gonna call this alpha. So what you get, u star is, now what if we call y over h, what if we call that eta? So that becomes eta plus alpha eta squared minus 1. And that gives you this kind of dimensionless velocity field that you can plot. So if we were to plot the velocity u star as a function of eta, okay, so we're plotting u star with different eta. So let's say this is 1 and this is 1. So at this point, eta is equal to 1. Remember, eta is equal y over h is equal to 1. So this means we are at the top of the channel, and eta equals 0, we are at the bottom of the channel. And u star equal 1, this means u wall is equal to u. So for when alpha is equal to 0, what we're going to get is u star is equal to eta. So we get this kind of straight line over here, 45 degrees, and this is your classic Couette flow problem. Now, when alpha is positive, so this entire quantity is positive, so that dp by dx is a positive quantity, this is where you're going to get some backflow. So you're going to start seeing profiles that look like this, depending on the value of alpha. And when alpha is negative, that means that the pressure at the entrance is larger than the pressure at the exit. You're going to get the kind of standard Poiseuille profiles. Okay, you get something like this depending on different values of alpha. And this gives you an idea about the combined Poiseuille and Couette flow. And you can do a similar analysis to find the volumetric flow rate using just this velocity field. You can do whatever you want with this. You can find the volumetric flow rate, the shear stress distribution, and you will notice that it's not going to be symmetric, but always at the point where we have the maximum velocity, we're going to have the zero shear stress. And then at the wall, we're going to have higher shear stresses. And depending on what the value of alpha is, you're going to have different distributions of shear stresses.